Hello, let's talk about explainability, Porcelli.
Yes, everyone's talking about AI, ML, and how to take advantage of that. But okay, but once you adopt, how you be accountable for what you're doing? How you
Many
learn what's happening behind the black box of AI and ML?
exactly, most of the time, especially for those who are here with us today, they're used of to invoking the machine, the AI/ML models, and then like what's going on in there. How can we understand what happens in that black box? So the good thing is that we have an expert here today to help us understand that.
Oh, yeah, that's great. Yeah,
So
our business automation group, our key group, has been investing on this for about 1 year and something, 2 years. And we have today a specialist on the topic, as you mentioned, Karina.
exactly, he's even a candidate for PhD. So he's studying that a lot, a lot, a lot. And Porcelli, he's the owner of one of our most popular videos about SHAP. So let's bring him. Hey, Rob, welcome. Thank you for joining us.
Hello, everyone. Thanks for having me.
It's a pleasure, my friend. And I'm actually pretty interested on what you have to present because you told us on the backstage that it's not going to be so technical that people who are not developers wouldn't understand. And also, it will bring some visibility to developers on how to interact with AI/ML models and understand what is going on there. Is that right?
Yeah, for sure. It's definitely a high-level sort of overview of what we offer, but with none of the boring details about how to actually do it.
But it's good that you mentioned this. We can try those things, right? So we have software available today in the Cogito ecosystem that is able to provide what you're going to show us.
Exactly. It's all open source and out there.
You know what? I will start your presentation in a second. But the thing is, making reproducing demos and copying and paste commands, that's the easy part. Understanding what actually goes what actually happens in there, the concepts and the things that are behind that, that is the key differentiator for you to actually have a system that does what you expect it to do. So Rob, tell us more about Trusty AI and how that can
Okay.
help us out. Okay.
Excellent. Will do. All right. So, hello, everyone. I've had my introduction already, but I'm Rob Giada. I've been working on the Trusty AI team for about, God, what month is it? November? 11 months now, since about December of last year. And I'll be talking about how the work that we do here ensures the fairness and transparency of AI and ML decision models. So before I get into any of this, before I get into any of this nitty gritty, we need to talk about, well, first I need to get my mouse over into this window. We need to talk about what AI is, because there's a lot of different interpretations of the buzzword AI. Like when I'm talking to people on the street, when I'm making small talk with my barber and I say, oh, I work in AI, they often sort of have this sort of wary reaction, being like, oh, aren't you afraid? Like, don't you think they're going to like escape? Like,
Do you talk about AI with your barber?
well, they're sitting cutting your hair. They're like, so what do you do? And I'm like, oh, I work in AI. And they say like, aren't you afraid they're going to like, break out, attack you, revolt, take over the world? And it occurs to me they think I mean this when I say I work in AI. Whereas if you talk to a mathematician or a statistician or a physicist about AI, you might get a slightly more derisive result. And so for our purposes, we're going to define AI as a combination of machine learning, so automatically extracting information from huge amounts of data, of digital decisioning, so trying to model human expertise at solving any particular problem, and math optimization to make all of the above as optimal and efficient and quick as possible. And so there's a ton of super cool applications of this, like just from things for things from around my own house, the things I use in my daily life that make my life easier or nicer in some way. And beyond these sort of, trivial and fun applications of AI, there's some that are truly transformative that can help a lot of people. But despite AI having these amazing applications, people are still tremendously wary. Like in this BBC article, this very BBC article, there's about a paragraph saying like, oh, this technology, it's amazing, it's impressive, it's going to save so many lives. The very next paragraph is assuaging people's fears about AI. And so the question I have is people right? Is the general populace right to be wary of AI? And I would argue absolutely. Absolutely, they should be wary of AI. And so I've got a couple of examples I pulled up of bad models that I've seen published and whatnot to give an example of why this transparency and why these explanations and why this fairness is important. So first up, we have Pulse. Now, Pulse has been going viral on Twitter as of late, or at least the circles of Twitter that I'm a part of. And what it is it's a technology to upscale low-resolution images via generative neural network into high-resolution images. And at face value, this appears to work great. Like, this does indeed look like the correctly upscaled image. But people started noticing when they released this publicly and people started playing around with it that you got some strange results. So if you put in, say, for example, a very famous low-resolution face, the output you got didn't match our expectation. Yeah, exactly. That's not right. But more sinister was people noticed that if you put in any non-white face, or the majority of non-white faces that were inputted, almost always outputted a white high-resolution output. And so this spawned a whole lot of articles about biases in machine learning, about what biases were present in this algorithm and what biases are present throughout the field. And the fatal flaw with Pulse was that the researchers that were designing it were not inclusive in the training data they were providing it. They didn't think about these biases. They weren't cognizant of the biases in their training data, didn't try and correct them, and thus produced a model that was highly biased towards producing white output and was not as inclusive as it needs to be. Next up, we have a traffic light classifier. Now, this is something I made specifically for this talk, so I can tell you all about how terrible it is with no real worry. What it is it takes in pictures of traffic lights, passes it through a convolutional neural network, and outputs a prediction about whether this light is red or green with a certain probability. So for this top picture, it thought it's red with 100% probability, and same goes with the bottom picture. It thought it was 100% sure it was a green light. And it does a great job of this. It gets 99.87% accuracy over the 10,000 test images I've evaluated it on. So that means it only ever made 13 mistakes. So it does a really good job. And we can even look at these 13 mistakes so these are the only mistakes this model has ever made. And they're not particularly egregious. Like, we might make these same mistakes. Like, a lot of these are like super ambiguous as to, like, I don't know, this bottom one with a red and green light. I don't know if you guys can see my mouse, but I'd have no idea what to do with that if I was an actual driver. So the fact that our model got that wrong isn't too troubling. So we might think this is amazing. Like, let's, put it in all of our self-driving cars. But there's a catch, right? We're going to perform a gradient-based adversarial attack on this model. And so what that means is we take a secondary auxiliary neural network and ask it to generate in addition to our original images, right? And so this is what our secondary, the attack model, has generated. And this is just what, to us, it looks like random noise. And I've upscaled the colors and the intensity of all of this noise by 10, just so we can even see it, right? And what we do is we add this random noise to our original image. And so that's what's on the right, is the original image plus that random noise. And if you've got a good enough connection to the stream, you might be able to see the difference between the left and right traffic light pictures. It kind of just looks like, JPEG compression artifacts. But so to us, that's still a red light, still a green light. But our model, the one that was 99.87% accurate, only made 13 mistakes, gets these completely wrong. It thinks that top image is 99% a green light. And so what this is an example of is a model that excels in the sterile laboratory conditions we've created, but in the noisier real world can be dangerously fragile, and therefore is a bad model. Finally, we have Genderify. Now, Genderify is probably the worst of all three of these. And what it was an API service that, given a name or an email, would try and predict the gender of the person that had that name or email. And so, ignoring how blatantly problematic and NB-phobic this is, just as a concept, like it's abysmal as a concept, people noticed a startling bias in it. which was if you put in, say, a female presenting name like Megan Smith, and it would output, 60% female was its guess. But if you put in Dr. Megan Smith, the probabilities would completely swap. And so this is obviously terrible. It's obviously incredibly biased. And likewise, this spawned a bunch of articles about bias in AI, with people even thinking that this was deliberately released as a joke because it was that terribly biased. And so this is another example of researchers not thinking about the biases in their training data, the biases that were used in creating their model. And by not thinking about these biases and by not addressing these biases, they propagate them forward. They train a model that has these biases, and that model reinforces them. And so this is something that you need to be aware of when working with AI and working with ML. We're aware of the biases, aware of how it works, aware of what it is doing to make sure you are not propagating things you do not want to propagate. And so in the Genderify case, it was released on like July 28th of 2020. And within 24 hours, all of these articles had come out and it was taken down. So thankfully, this only lasted about 24 hours out in the wild. But there are AI models that do not get this scrutiny, that aren't as public, that continue to operate and continue to propagate harmful biases. And so with these examples, the question is, well, what protects us from bad models? And from a surface level, in our first line of defense are regulations. Now, a lot of countries and regions are producing regulations to keep us safe from AI. Like we have Europe's GDPR, we've got the UK 2018 Data Protection Act, and a lot of American states are coming out with their own individual regulations. And the interesting thing about all of these is that the way that these laws are keying in to keeping us safe from AI is by looking and entitling us to explanations about how the AI is working. So that the way that the law thinks to regulate AI is to enforce it to be accountable. That AI cannot be some deity in the sky that comes down and says, this is my decree. You have to be able to ask it why. It has to be transparent and accountable. So the thing that makes that difficult is if we look back at AI, we look back at this composition that is AI, well, digital decisioning is relatively easy to explain and interpret. Like it's modeling human knowledge. For us to have modeled human knowledge in software, we had to have understood that human knowledge to begin with. But these other two can be tremendously opaque. And so that's where Trusty AI comes in. Now, Trusty AI is part of the Cogito family of applications. It's a cloud native platform. And Trusty AI is designed to be run in sort of container environments like Kubernetes and OpenShift. But for exact details of how you actually work and deploy with this, you'd have to speak with the people that work and deploy with it. I'm more of a mathematician myself. But Trusty AI offers three main services with more on the way. We have runtime monitoring, which is all about looking at metrics of our models. We have an Audit UI, which is about designed to look at the history of models. And we have an explanation service to provide explanations for the decisions that models are making. So let's look at all of these in some more detail. So runtime monitoring. This is all about metrics, and it's divided into two categories of metrics. First, we have business monitoring. So this is all about how the model is applied. It's a real world business use case. So things like tracking metrics about what sort of outputs it's producing. Like if we have a loan application model, like how many acceptances and how many rejections is it outputting? To monitor metrics about what sort of inputs are we getting? Like how are users using our model? What sort of things are they expecting of it? And how these things might be changing over time. And then we have operational monitoring. And these are about engineering metrics. So the things that our engineers would want to see as they're running their models to make sure that they're working appropriately. So things like, its prediction runtime, its latency, the load the system is getting, the health of the cluster it's deployed on, stuff like that. And so as an example of why this is all necessary, these metrics are necessary, let's look back at our traffic light classifier. And we can think, what might we want to monitor? What might we want to have real-time visualizations of to make us to have more trust in our model? And so from a business monitoring perspective, some things I would want to see is the average prediction confidence at any given time, because we'd want to make sure our classifier was confident that of its predictions. We'd want it to say this is 100% a red light. We don't want it unsure. We'd want to see, say, GPS locations of low confidence predictions throughout, say, the city we're trying to deploy this technology in. Because if there's certain areas that it has low confidence in, we can't deploy this technology. We need to know that everywhere in, say, the city we're deploying it in, say we're deploying it in London, we have to know that this works everywhere in London. And we need to be able to see quickly where it's not working. And finally, we might want to look at the agreement rate between different vehicles. Say, like, two vehicles equipped with our classifier are at the same intersection at the same time. We want them to see the light the same way. And if they're not agreeing, we have a fundamental fatal flaw. Next, we can think about looking at prediction latency from an operational monitoring side of things. That we want to see how long it takes for predictions to get through our pipeline from start to finish. Because if it takes 5 minutes, that's not going to work. Like, if it takes 5 minutes to say this is a red light, we've already gone through the intersection and crashed into someone. Or we might want to look at, say, the hourly load. Like, how many queries are we getting in each hour, so that at rush hour we can have sufficient scaling capabilities. So all 5 of these metrics are things that we'd want to track live throughout development, throughout design, throughout testing, throughout deployment, to make sure that our model are hitting the criteria we establish for being operational. Like, all of these we need to see are sufficiently good before we can put this out into the wild. And so once in testing we have found that our model meets the criteria we've set out, we've watched these metrics, we're happy with these metrics, we can have trust in our model that it's doing what we want it to do. And when we have trust in our model, we can advertise that trust in our model to customers, to clients, to the general public, that, our model does all these things. We know it does. We've seen it do it. Let's sell it. Okay, next we have the Audit UI. And so the Audit UI is all about history, all about tracking how the model has made decisions over its lifetime. So it keeps a log of every decision the model has ever made. You can investigate previous decisions. You can see how the model was running, see the status of those metrics as the model was making those decisions in its history. And so why is this important? Well, let's run through another example. Say a vehicle with our traffic light classifier has been in a minor accident, an fender bender. What we can do is we can open up the Audit UI to examine the decisions that led up to the crash. Right. And so let's say we'll pull up the last images it saw like 10 seconds before the impact. Right. So we look at those inputs, and this is the last light that the car saw. Right. We can go and look. We now know this is what the input was because we found it in the Audit UI. We'd go look at the model's prediction for that input, and we saw that it predicted 100% green. So we can see that the model saw the light correctly. So whatever caused the crash, it wasn't us. It wasn't the traffic light classifier. Alternatively, maybe it saw the light wrong, and we can take the appropriate actions. Now, the reason that this is important, the reason that this is useful, is if we think back to those regulations we were talking about. For example, like in GDPR, the data subject shall have the right to obtain meaningful information about the logic involved with any AI decision. Like, if an AI decision affects them, they have the right to know why. Why did the model make that decision? And if you don't have an Audit UI, all the decisions made by your models are completely transient. They're made and then they disappear. And so if someone comes up to you and says, I applied for a loan, I didn't get it, why? If you don't have an Audit UI, you cannot answer that question. You cannot comply with the regulations. Meanwhile, with the Audit UI, it's as simple as saying, oh, John Smith, November of 2017, here's all your information. You got denied for your loan because your credit score was 6. You have all of that information in the Audit UI, and so you can comply with these regulations that you must comply with to use these AI decisions. Okay, and finally, we have explainability. So explainability is my little corner of the team. I work in explainability research, and so it's what I know the most about, and so it's what we're going to go into the most depth of. So explainability is all, it's very well named. It's all about explaining model behavior. So given some, there are inputs to our model and the decision made, we want to know why this decision. What made you make this decision? And there's a couple of ways of approaching this, right? We can look for a local explanation, i.e., given this particular input, what parts of it led you to this particular decision? Or we can look for a global explanation that given trends and distributions of the inputs, how did those trends and distributions affect the overall category of decisions you've made? What trends in the inputs affected trends in the outputs? But the thing with both of these frameworks, local explanations and global explanations, is that the way you go about answering this question and how easy it is to answer this question is highly dependent on what's inside the model. Because if our model is, a flow chart, it's really easy to explain its behavior. Why couldn't I log in? Well, your password was wrong. Or if it's a simple equation, you can just look at it and know why it's doing what it's doing. But if your model is a deep convolutional neural network, you're not going to be able to look at it and know what it's doing. Or alternatively, it could just be locked behind a REST API that you just, ping off. It's in the cloud somewhere and it sends you back its results. You have no idea what it is. It could be a person typing back. It could be a neural net. You have no idea. And so at Trusty AI, all of our explainability methods have to be model agnostic. They cannot have any information about what the model is because we might not have that information. So we can't make assumptions about it. And so the way a model agnostic explanation works is it's a very pragmatic approach. It's like trying to figure out how your new smart toaster works. You just sit there and you poke around the buttons, and by observing what happens when you poke the buttons, you can observe how what happens to your bread, and you can figure out how the machine works. And it's the same idea with model agnostic explanations. You poke around with the input enough, and by observing how it affects the output, you can get a sense of how the model works. And so we have 3 model agnostic explanation techniques within Trusty AI, and more to come. It's an active area of research. First, we have LIME. Now, LIME comes from a 2016 paper out of the University of Washington, and it stands for Locally Interpretable Model Agnostic Explanations. And so LIME is best explained and best understood through an example, right? So imagine we have a model that classifies points into this Cartesian space into either red or blue, right? And we want to explain why this point was red. Now, globally, over this entire plane, it's a very complicated decision boundary. Like if we move the point in either direction, the decision is going to flip multiple times. Like, I've lost my mouse. If we move the point further right, it's going to be blue, and then further right again, it'll go back to being red, and then blue, and then red, and then blue again. Meanwhile, if we move the point around in a complex path, it stays red the entire time. So it's, the global decision boundary is really complex, and its position isn't sufficient to tell us why it's red, why isn't it blue, because it has such a complex decision boundary. However, rather than focus on this massive decision boundary, what if we just focus on a little local area around our point? And in this little local area, suddenly the decision boundary is really simple. Left is red, right is blue. And so that's exactly what LIME is trying to do. What it does is, given the point we're trying to explain, it generates a bunch of sample points in the local neighborhood around our point, passes them through the classifier, and then tries to establish a linear boundary between the two that separates red from blue, separates accepted for alone and not accepted for alone, whatever decision your model's making. And when we have a linear boundary, we can make a linear equation, where the weights of our linear equation are our feature importances, i.e., how much each component of our input affected that decision boundary. Now, due to specifics of the mathematics of this, the exact values that are produced in these feature importances aren't as important as their relative magnitudes. What does that mean? Well, it means that LIME produces an ordinal ranking of the importance of each input feature to the model's decision. So it answers questions like, what features were the most important? Which features didn't really affect the result? Which features were least important? Qualitative analysis of how important features were is what can be provided by LIME. Okay, next we have counterfactuals. Now, counterfactuals approach the explanation problem a little differently. So say we have an input and a decision, but we're not really happy with the decision we got. We really have something else that we would have preferred to get. What counterfactuals seek to do is find the nearest valid input that would have got us that desired decision. So let's look at an example of this to see what that means, right? So say we are applying for a loan. My name is Rab Giada, I'm 26, and I'm applying for a loan of £100,000, right? I send that to the bank puts it through their loan application model, and they deny me. And I want to be approved. That's my desired outcome, is to be approved for this loan. And I asked the bank, well, what could I have done better? And the bank can pass my data point through their counterfactual explainer, and it'll try and produce the nearest valid input that would have approved me for the loan. So what does nearest valid input mean? Well, if we think about it, it needs to be close. Like, I can't change too much about myself to get this loan through. And there's only a few things that are valid of ways to answer these questions. Like name, for example. I don't have a lot of flexibility in how I can input my name into this model, because I'm not going to change my name for this loan. I don't want it that much. Same goes with age. Like, I can only change that in one direction, unfortunately, and the direction I can change it in only moves one day at a time. So I don't have a lot of flexibility in changing my age for this application. But amount, I have flexibility. I can ask for less, I can ask for more. There's a lot of valid amounts. And so given these valid ranges, these constraints for the features, a counterfactual explainer can try and find a point within this space that's close to my original input that gets me approved. So say, for example, 70K would have got me approved, and that would be the nearest valid input to my original input. And so the interesting thing about counterfactuals is more specifically the way that we've implemented them in Trusty AI. So we look at this overall sort of framework of how a counterfactual works, right? And then we just like rename some of these components. Like, instead of a counterfactual explainer, we have a cost function optimizer. We have a problem instead of a model, and we have solutions instead of outputs. We realize that this is just a constraint solving problem, and we can use Red Hat's in-house constraint solver to do all of this. And so that's exactly what my coworker Rui Vieira has done. He's the guy in charge of implementing counterfactuals. And he's made an excellent video about the maths of counterfactuals and how OptiPlanner factors into all of it. So if you're interested in that, you're interested in seeing how we use OptiPlanner, interested in counterfactuals because they're super cool, check out that video. You can get the slides after the stream. But in summary, counterfactuals tell you the minimum input changes you need to get your desired results. So it answers questions like, is it even possible for me to get the output I want? How close was I to getting what I wanted? Okay, and finally, we have SHAP. As Karina said, this is the thing that I'm in charge of. I'm the one that writes the SHAP implementation, so I'm super excited about it. But SHAP comes from a paper in 2017, also out of the University of Washington, and it stands for Shapley Additive Explanations. So the way that SHAP approaches the explanation problem is, given an input in a decision, it asks for a set of sample representative inputs called the background, the typical inputs that the model usually gets in its operation. And then it passes these background points through the model to establish the average background decision as a reference point. Like, if we know what the sort of average output of the model is, we can then use that as a reference point to make comparisons. What we then do is create a bunch of permutations between this input and the background. We smush them together. We take parts from the input and put it in the background points. We take background points and put it in the input to create a bunch of hybrid data points called the synthesized data, the synthetic data, that are combinations of our original input and the background inputs that we collected. We then pass these through the model and observe the decisions made from these synthetic data points. Specifically, we observe how those decisions compare to the average background decision. Then what we can try and do is create a linear model that emulates these synthetic decisions. And if we're very, very, very careful on how we create this model, we can make sure that these weights in this left-hand side of the equation are Shapley values. Now, Shapley values are a concept from game theory that are super cool. They have a bunch of really, really cool properties, but I'm not going to get up into detail of what they are and the maths of them because it's a little dense. But basically, provided our weights, provided those W's are Shapley values, we can then recover the exact contribution of each feature to the output. So what does that mean in practice, right? So say we are value. We want to get a value of our car. We have a Ford Focus. It's 5 years old. It's got 60,000 miles, and it's got a very good interior condition, right? We pass it into a car valuator model, say on autotrader.com or whatever, and we get outputted that it has a value of £20,000. And we want to know why. Well, we can run SHAP in that, which will try and then produce a linear model that emulates the car valuation model. And by running SHAP, we will get our explanation. And what SHAP produces is the exact contributions each feature had on the output of the model. So for example, the SHAP value for age happens to be negative 10,000. That the age of our car subtracted 10,000 as compared to the average car. That the mileage subtracted 5,000 compared to the average car. That the interior quality increased the value of our car compared to the average. And so that's the idea with SHAP. It gives the exact contributions each feature had on the output. So it answers questions like the same ones as Lime, like which features contributed most positively or most negatively. But since the values are the exact contributions, you can get an itemized account of each decision, almost like a receipt. You can get a complete breakdown of how each feature contributed to your output. So if you want to know more about SHAP, the maths of it, more about Shapley values and how it all works, I made a video on the Key YouTube channel that you can check out following this QR code if you, again, want to download the slides after the show. And so in summary, for the explainability, we have Lime, which gives you relative importances of each feature. We have Counterfactuals, which tell you how close were you to the outcome you wanted and how you might go about getting the outcome you wanted. And we have SHAP, which gives you the itemized breakdown of how much each feature contributed to your decision. And so in recap of the things we've talked about so far, we've got runtime monitoring for live monitoring of metrics of your system. We've got an audit UI, so you can see the history of every decision your model has made and information about each of those decisions. We've got the explanation service that provides explanations of any decision your model makes. And so the question is, well, what's next? And if you remember back to the title slide of this presentation, I talked about the transparency and fairness of AI ML models. And I've talked a lot about transparency, but haven't really mentioned fairness. And that's because fairness is what's next, or it's what we are thinking about doing next, thinking about implementing next. And so the question is, given an input and a decision, well, did our model treat that input fairly? Was this a fair decision that was outputted? And you might think, well, what does fair mean? And in AI ML context, that's a very complicated, nuanced question. And there's a lot of different definitions of fair. Say, for example, we have a model, right? And our model takes as input, a big long input, but one of those features within our input is a protected attribute, something like, sex, gender, age, race. We can define a fairness metric called demographic parity, where a model with perfect demographic parity produces the same decision distribution regardless of your value of your protected attribute. So regardless of whatever particular protected attribute you have the same likelihood of getting any particular decision. So say, for example, a loan applicator application model would have perfect demographic parity as if regardless of protected attribute, regardless of your race, you'd have the same likelihood of acceptance or denial. On the other hand, we can have equality of opportunity as a different fairness metric, where this is more concerned with the performance of your model, that regardless of your status in the protected attribute, you are entitled to the same model accuracy, that regardless of, say, your race, you are just as likely to be a true positive or false negative as someone of a different race. And so these are just two fairness metrics of many different ones that are defined in the literature. And when you'd want to use each of these metrics is sort of a nuanced question, depending on your specific model, your specific application, your specific user base. And so TrustyAI's goals for fairness are, well, given any arbitrary model, can we quantify its fairness via the appropriate metric? And if that model is unfair, is there anything we can do to transform it automatically into one that is satisfactorily fair? But these are all research topics on the far horizon that we are just sort of discussing in blue sky meetings.
But is this something that is being discussed across the community, or is it just being investigated internally on how we can actually solve it?
these are right now, this is very, very, very preliminary things that we were talking about in research paper meetings, and less so in terms of concrete roadmaps. But this is at least our fairness is one of the topics on our research calendar, on our research radar of what's up next for us to be researching and playing around with. And so that is all I have for the talk. If you guys have any questions, I'd shoot me an email, talk to me right now. I'd love to hear it.
It was a fantastic presentation, Rob. Thank you very much.
I love it too, the way you expose these complex topics in such an easy way to understand. Thank you so much for bringing this to the KIELive. I bet this is a basic video for everyone who will start using Trusty AI and explainability through the Cogito application. So thank you, Rob.
Thank you.
Yeah, and one thing that I can mention that soonish we will see is the same way that we have the dev UI for the process side. We are working to incorporate the trusty capabilities of some of this audit UI that Rob mentioned that we have today in the Trusty AI console as part of the dev UI experiences. So you'll be able to get your models that you have there and run and try with the audit UI, integrating the dev UI. So you, as a developer, you have this tool. You don't need necessarily to deploy a model in your console in a different place. That's a team is working right now as we speak, and I think it will be very valuable for explore this technology. That's fantastic.
Yeah, the thing there is that you mentioned Trusty AI a lot. So Trusty AI is actually the effort that we have here in the key group, right? And then from this effort and all the studies, we are creating tools to support it. Is that correct?
Yeah, definitely. All of this is meant to be stuff that you'd interact with in a production environment. That it's designed to be tools that we're releasing to the community to be used by customers, by users, for sure. It's all concrete implementations.
The thing is that it's fantastic that you can just explore all of this to actually add such an important value to business automation. So yeah, I love it. Thank you so much. All right. So Rob, any last thoughts?
No, nothing off the top of my head. What Alex was mentioning about having all of these tools integrated into a development environment is, I think, massively, massively important, especially if we think about back to the bad models I was talking about. One of the biggest problems with those models was that when they were being designed, these sort of things were not crossing the minds of the developers. That they were not thinking about biases. They were not thinking about explanations. They weren't thinking that if they looked at Dr. Megan Smith in their input, that their model was keying onto doctor in its prediction, not Megan Smith. And so having these tools right there with you when you're designing your models is so important. So I'm so glad to hear that that's part of the roadmap, to bring this as close to development as possible.
Exactly. Because as we can incorporate in the life cycle development, not as a second moment. So when you get close, you can avoid so much of these pitfalls early in the cycle development.
Love it. Okay, so thank you, Rob. I hope we can see you again here soon.
Yeah.
Thanks so much for having me.
Okay, bye, Rob. Guys, so thank you so much for joining us today, and I hope we can meet again on the next KIELive session. Bye.
See you. Bye. Like and subscribe.